Okay, for this problem, we were given this rational function, 2x plus 9 over x squared minus x minus 6, and we're asked to use partial fractions to find the Taylor series expansion about x equals 0, and then use that expansion to figure out what the second derivative at 0 is. All right, now I'll say that, of course, we could find the second derivative directly using the quotient rule. It's not that hard of an exercise. It is somewhat time-consuming. Okay, so let's use partial fractions to find the Taylor series. So first tip off is to find the Taylor series expansion, or the partial fraction expansion. So x squared minus x minus 6, the denominator factors as x minus 3 times x plus 2. So I have distinct linear terms, and so I should write this as a over x minus 3 plus b over x plus 2. And so I've got my equation 2x plus 9 is going to be equal to a times x plus 2 plus b times x minus 3 after I clear out the denominator. Okay, so now I plug in numbers in order to figure out what a and b are. So let's let x be equal to 3. If x is equal to 3, on the left side, I have 2 times 3 is 6, plus 9 makes 15. If x equals 3, I've got 5 times a. And then if x is equal to 3, this disappears, I get 0. So 15 is equal to 5a, and therefore a is equal to 3. The other thing that I could plug in that would make sense would be negative 2. If x is equal to negative 2, on this side I have negative 4 plus 9 makes 5. If x is equal to negative 2, I get a 0 here. And if x is equal to negative 2, I have negative 2 minus 3 makes negative 5b. And therefore, b is equal to negative 1. Okay, so coming back up to the top here, therefore, 2x plus 9 over x squared minus x minus 6 is equal to 3 over x minus 3. Then I have minus 1 over x plus 2. Okay, and now I need to find the Taylor series expansions for this. Now, the way that I will do this is I will use the known expansion that 1 over 1 minus x is equal to 1 plus x squared and so on, or summation n equals 0 to infinity x to the n. And that converges as long as x is between 1 and negative 1. Okay, now to use this formula, I basically need to make sure I have a 1 in front. So let me rewrite these so that the constant term's in front. So just doing a little bit of algebra first. Let me multiply top and bottom here by negative 1. So negative 3 over 3 minus x, multiplying top and bottom by negative 1. And on the second term, let me just switch the order, 2 plus x. Okay, now to force a 1 to be in front, let me factor out a 3 from the bottom, 1 minus x over 3. And for the second term, let me factor out a 2, 1 plus x over 2. Okay, and so before I use the Taylor series expansion, I can cancel the 3's here. So I've got negative 1 over 1 minus x over 3, and then minus a half times 1 over 1 plus x over 2. Okay, and so now I can employ the expansion that I see here. 1 over 1 minus x over 3. Everywhere I see an x, I replace by x over 3. So I've got negative summation n equals 0 to infinity of x over 3 to the n. The second part, I have minus 1/2 times summation n equals 0 to infinity. Everywhere I see an x up here, I replace by negative x over 2. So negative x over 2 to the n. Okay, so now I can combine these. So summation n equals 0 to infinity. I've got negative x to the n over 3 to the n. Then I have minus 1/2 times negative 1 to the n, x to the n, over 2 to the n. All right, so I'm almost got it. So summation n equals 0 to infinity of, okay, so x to the n is common to both, so I can factor that out. So I have negative 1 over 3 to the n. Over here, I have minus negative 1 to the n over 2 to the n plus 1 times x to the n. And perhaps I can simplify that a little bit, but basically that's it. That is the Taylor series expansion for that rational function. All right, now let's talk about convergence. Here, this converges if two things happen. We need x minus 3 to be between negative 1 and 1 in order for this to work. And we also need x over 2, negative x over 2, to be between negative 1 and 1. All right, this first inequality is negative x has to be between negative 3 and 3. And we also need to have that x is between 2 and negative 2. If I multiply by negative 2 and change inequalities and then flip it back around, that's that. All right, so I need to have x between negative 2 and 2. I also need to have x between negative 3 and 3. So if x is between negative 2 and 2, this is redundant. And so this converges for x between negative 2 and 2. All right, now the last part of the problem that we're supposed to find is that we needed to figure out the second derivative at 0. The second derivative at 0. Okay, so let's take a look at the second derivative. Okay, so the Taylor series expansion is summation n equals 0 to infinity of the nth derivative at 0 divided by n factorial x to the n. So let's take a look at the x squared term. From here, the x squared term is the second derivative at 0 divided by 2 factorial x squared. From here, the x squared term is going to be, well, what do I get when I plug in n equals 2? I get negative 1/9 minus negative 1 squared over 2 to the third, x squared. And so I have that these two things have to be equal. And so that means that f double prime of 0 divided by 2 is supposed to be equal to negative 1/9 minus 1/8. And so solving, that means that f, the second derivative at 0, is equal to negative 17 over 36 after I get a common denominator. Okay, so that is the second derivative at 0. And again, this exercise is to emphasize the intuitive interpretation, the definition of a Taylor series.